Hi, my name is Izna Anadra binti Syari Zaham and I'm from G2. Today, me and my teammates would like to present to you on our project on wafer fabrication using CMOS technology. Wafer fabrication is a fundamental process in semiconductor manufacturing where a pure silicon wafer is transformed into integrated circuits. These integrated circuits are used in many modern electronic devices such as smartphones, computer and embedded systems. The objective of this fabrication process is to produce devices that are reliable, efficient and low power consumption. To achieve this, multiple layers of materials are formed and patterned on the silicon wafer. These layers create important components such as transistor, interconnections, and insulating regions. Several key processes are involved, including oxidation, photolithography, etching, doping, and metallization. Each process must be carefully controlled because even a small variation can affect the final device performance. In CMOS technology, both NMOS and PMOS transistors are fabricated on the same substrate. To allow this, special regions called wells are created. For example, an N well is formed to build PMOS transistor, while NMOS transistors are formed directly on the P-type substrate. Overall, the wafer fabrication is a complex but highly structured process that transforms a simple silicon wafer into functional electronic device.
I will now explain the PMOS fabrication process and its components. PMOS stands for P-channel metal oxide semiconductor transistor. It operates using holes as the majority charge carriers and is usually formed inside an N-well region. The fabrication process begins with oxidation, where a silicon dioxide layer is grown on the wafer. This layer acts as an insulator and protects the surface. Next, photolithography is used to transfer patterns onto the wafer using ultraviolet light and mask. After that, doping is performed to create P-type regions for the source and drain. Etching removes unwanted materials and metallization is used to form electrical connections. A PMOS transistor consists of several important components. First is the substrate, which supports the entire structure. Then, we have the N-well region where the PMOS is formed. The gate oxide is a very thin insulating layer that separates the gate from the silicon surface. On top of it is the gate electrode, which controls the transistor operation. The source and drain are heavily doped P-type regions that allow current to flow. Finally, metal interconnects connect all components together in the circuit. In operation, when a negative voltage is applied to the gate, a conductive channel forms between the source and drain, allowing current to flow. When the voltage is removed, the channel disappears and the transistor turns off. This switching behavior is essential for digital circuits.
Hi, Assalamualaikum. I am Siti Rozani binti Abdul Razak and now I will explain the fabrication process and methodology step by step. The process starts with a silicon wafer produced using the Sawatsky method. This wafer acts as the base material for the entire device. Next, a thick silicon dioxide layer is grown using wet oxidation. This layer serves an insulation and protects the wafer surface. A photoresist layer is then applied using spin coating to ensure uniform thickness. After that, photolithography is performed using UV light and a mask to transfer patterns onto the wafer. This exposed oxide is removed using the etching solution and the remaining photoresist is stripped away. Boron diffusion is then carried out to introduce P-type dopants into the silicon. This step is important for forming semiconductor junction. This step coating, exposure, etching and cleaning are repeated multiple times using different masks to gradually build the device structure. Later, a thin oxide layer is grown using dry oxidation for better control and precision. Finally, aluminium is deposited using the sputtering process to form metal interconnection. Another photolithography step defines the metal pattern, and unwanted aluminium is removed through etching. At the end of the process, the wafer contains a complete device structure ready for testing.
Okay, now I will present about the result, application, and conclusion. For the final wafer, we observe the information of aluminium contact pads. These pads are used for electrical connection, testing, and integration with external circuit. That results show us the combination of oxidation, photolitho, doping, etching, and metallization successfully creates a functional semiconductor structure. CMOS technology has many important applications. It is widely used in microprocessors and CPU, where it enables fast and efficient competitive. It is also used in memory devices such as RAM and flash memory. In addition, CMOS is essential in digital logic circuit, mobile device, image sensor, and low power electronics. Its ability to reduce power consumption makes it ideal for modern portable device. In conclusion, wafer fabrication is a highly used, precise and complex process that requires strict control of all parameters. Factors such as oxide thickness, doping concentration, and alignment must be carefully managed. Any small error can lead to device failure or reduce performance. Therefore, fabrication is carried out clean room environment to ensure accuracy and reliability. Overall, this project helped us understand the importance of precision and process control in producing high performance semiconductor device.